Right, year 12. This is, as promised, a commentary on the Bristol special sheet, which you looked at for, well, just before the Easter holiday, actually. So I'm just going to comment on the three areas which were on Insight, and I think I asked you to look at the overall outcrop pattern of the rocks, the major structures that you could see on here, and then look particularly at the relationship between the Triassic rocks and the rocks that were underneath them, beneath them. Okay, so let's look at the overall outcrop pattern. And what you've got is you have got rocks between Devonian age, which are broadly these sort of reddish ones here. You've got Carboniferous rocks, and then you've got the lighter browns of the Jurassic and the Triassic above that. The overall outcrop pattern reflects the structures that you can see on the map. So the dominant structure on the map is obviously this structure here, which is clearly an anticline. It has got older Carboniferous limestone in the middle, and then newer Carboniferous limestone on the limbs of the anticline. So we're going across both sections A and B of the task that I asked you to do. Above that, you have then got Triassic rocks, which lap around here and come across here and come across here, and then Jurassic rocks, which are mainly up in the top part of the map, the northern part of the map there, and you get a little patch there of Jurassic rocks appearing beneath this younger drift on the southern side of the Mendip Hills. Let's look at the dominant structure. The dominant structure is this anticline, which you can see a northern limb there, steeper, and a southern limb here. And in fact, this is the same fold. The axis is bent, and the axis also goes in 3 dimensions through a sort of a whale, a swale really. So here, if you look at the dip arrows, close to the axis, they are showing the fold plunging to the west. Here, where we get the limbs, the axis coming through, the dip arrows plunge to the east. So this axis is kind of riding a bit of a roller coaster. It's going into a dip and then coming up on this side. So that is a major east-west trending anticlinal axis with a steep limb to the north and a gentle limb to the south. Steep limb to the north, gentle limb to the south. You can tell the dip of the rocks on the limbs because you look at the dip arrows and also look at the breadth of the outcrops. And the relationship is always this, that the shallower the dip, the broader the outcrop on the map. So on the steep limb, I think the dips are at about 50 degrees, and you can see that the outcrop of the limestone is narrow for each section. On the gentle limb on the southern side, the outcrop pattern is much wider. If you look at the Triassic rocks, they are gently dipping across the whole of the map. You've then got some faults, which, for example, these ones down here and these ones, and there are various other ones, and they are thrust faults. And they have been caused during the compression that caused this folding, and this is what's called a Hercynian fold. It was formed by a mountain building event which occurred during the late Carboniferous. So the youngest rocks that have been affected are Carboniferous rocks. The Triassic rocks above those, or on top of those, are not affected by that Hercynian folding because the mountain building event had occurred by then. So you've got thrust faults caused by the compression. Some of those are reactivated as normal faults as well, but they match in with the trend. The structural trend is still more or less east-west, all right, it's a bit northwest-southeast here, but it matches with the flow of that axis. You can see various faults, and on the bigger, the main sheet, you can see lots of faults like that. Contrasting with that, you have got other faults which clearly cross-cut and affect younger rocks entirely. So there's more than one session of faulting here. Those younger rocks are not compressional features at all. They are normal faults. They are extensional later features altogether. So the Triassic rocks are very, very gently folded. They're hardly folded at all. The dips are probably less than 10 degrees, probably well below that in most cases. And the same for the Jurassic rocks. You can see a little bit of folding down here. There's an anticlinal axis, but it's very, very small scale, very gentle, open folding. So clearly there's a period of earlier deformation at the end of the Carboniferous, and then some later folding and faulting, which is on a much less impressive scale. Let's come down to the relationship between the Triassic and the rocks below the Triassic. And here's the interesting bit of the map, the really interesting bit of this section of British geology. This is a really good example of what's called a palimpsest landscape. So the folding at the end of the Carboniferous caused uplift, and the uplift resulted in erosion. And this was a mountainous area, and they were very large scale valleys eroded through the Carboniferous limestone once all that erosion was taking place. And then, after the end of the Paleozoic, rocks were deposited in Triassic times on top of that undulating landscape with big valleys and big hills in it. And you can still see that palimpsest, that fossil landscape. Here's the evidence. There is an unconformity that runs at the base of the Triassic. These features cross-cut the Carboniferous beds, and everywhere where that happens, you are seeing a valley in that Triassic landscape, which is being infilled with Triassic alluvial conglomerates and sandstones deposited in a desert environment. It's the same on the southern edge of the map here. Here we go. Here are the palimpsest valleys. The relative relief, in other words, the depth of the valleys, is quite often tens or even 100 meters or thereabouts. They're really big features which are cutting back into the limestone hills. Here we go, all the way along here, and then on the crest of the hills themselves, you've got older rocks revealed in the core of the anticline. So the picture to have in your mind is of a ridge built in limestone mountains, and then the Triassic rocks are taking bites out of that, if you like. The erosion at Triassic times is taking bites out of that, and then the eroded material from the limestone hills is infilling those valleys with alluvial fans and rivers flowing off to the south and flowing off to the north. And if you look at the content of those alluvial fan conglomerates, the dolomitic conglomerate, F6 as it is on the map, then you can see that lots of the eroded material actually has Carboniferous limestone fossils, trilobites and corals and brachiopods and bivalves, all deposited close to the source of the rocks which were being eroded from the highest parts of those mountains in the Mendips. And those clasts are deposited in the alluvial fan conglomerates and breccias there. So a fantastic piece of British landscape and geology. The valleys which are being exhumed here, revealed by erosion in modern times, those valleys are at least 200 million years old, and probably older than that. So you are starting to see the skeleton of a palimpsest landscape dating from Triassic times, and it's emerging from beneath younger rocks. You're seeing a window into the past, and that is an absolute classic piece of British geology. So if you get a chance, pick up a copy of this Bristol special sheet. There's lots of other interesting geology on there, including an unconformity at the base of the Devonian as well, when there's a major mountain building event, the Caledonian mountain building event. So your sub-Triassic unconformity, sub-Mesozoic unconformity, isn't the only major one here. There's another one, much older, and then in actual fact you do go down into Precambrian rocks on the Bristol sheet, because there's the Tortworthy inlier to the north of Bristol. So you can see the basement rocks too. I'll talk a little bit more about that, provided we get to meet on Teams. I'll put a link to this video on Insight. Enjoy your geology. Thank you very much for listening.